Alright, so what I'm going to talk about today is a technique that you might like to employ when you're doing experiments. This course is titled Measurement and Design. So one way of measuring something is observing. And you can observe things in different ways. You can observe with your naked eye, or you could have assistive devices that can aid you in visual observation. And one of those assistive devices, you could have a microscope, you could have a telescope, a rangefinder, but a really useful instrument that is now used as a household item is a camera. A camera can record a video, it can take images. So how can we use a camera to observe something? And the great advantage of using a camera is that all the data is digital, videos are digital, and so are images. And this digital data provides a very rich repository to be processed. So remember, when we started our course, we were talking about measurement really means data to decision. So a very rich source of data is visual data. So one technique that you would like to employ is fusing video data or image data with physics. And that's what I'm going to show you today. And you'll be left with a homework problem, which you'll probably do on your own. You don't need to come to the lab for that homework problem. So let me state the homework problem up front. The homework problem is that you look at any phenomenon in which there is some motion. Motion in the language of physics is called kinematics. So any phenomenon which has some moving parts, for example, a bouncing ball, an insect moving, a bird taking flight, two objects colliding with one another, a person walking, the gait of a person, and so on and so forth. You could take a video in the squash court, in the tennis court, in the playground, a child on the swing, any video that you like. You could even take a video from the internet and employ some of these techniques and submit a 2 to 3 page report of what you've done. Okay, so I'm going to walk you through today of what is possible with video tracking. Alright, so for video tracking, our solution, there are many solutions out there which are softwares that can take up a video or an image, and then you can get trajectory data out of that video. So basically what we need is to identify a moving part in a video or an image and convert that moving part into positional data with time. That's all you need. So once you have positional data, you can take derivatives and find speeds. You can take higher order derivatives, find accelerations, and other higher order terms as well. And you can find angles. Once you have the geometry in front of you, you can define angles, you can define angular speeds, and so on. So mainly you need positional data. So the different softwares exist. One of the very popular software that is used worldwide is called Tracker. It's open source. What we will employ is software that we've written. It's in MATLAB. It's called PhysTrack. It can be downloaded from this website. And I'll show you how it works. Okay, but feel free to use any software you like. Just to give an example, the great thing about physics and video tracking with physics is that apparently very simple phenomena, once you look at those phenomena through a camera, a new world of opportunity opens up. There are twists and turns and motions that are imperceptible to the naked eye. But once you get positional data in the form of a stream or a sequence of images, that positional data can reveal many other nuances in the motion that will otherwise remain hidden. Just an example is this coin that is being doubled around on a flat surface, and then you have a high-speed camera that captures this video. Now, this is a seemingly innocent process which does not have a life on its own, but once you track this, you can do a master's level or a PhD level thesis on this motion. It's extremely complex. Many years ago, I came across this slide, this picture from some movie, and I do not recall the name of the movie itself, but I was intrigued by this. She's an actress and she's in some kind of homegrown laboratory, and she has this strange object in front of her. It's an inverted cone made of metal, and I really, at that point, probably she's boiling something. But at that point in time, I was wondering to myself, what would be the purpose of such a cone, a metallic cone? And how did the producers or directors of this movie come up with this idea of showing an inverted cone? Many years later, which is around 5 or 6 years ago, I actually employed such a cone in one of my experiments. Okay, so now this is a real cone, must be lying somewhere around. It's a real cone. This is a brass, it's a brass cone, and I hang it, suspend this from an object, from a suspension. And this person here, my colleague, is wearing some gloves and is pouring some liquid into this cone. So this liquid is liquid nitrogen. Alright? So once liquid nitrogen goes into this inverted cone, let's see what kind of phenomenon do we observe. So I'm going to play a video here. Alright? So on the left side of the screen, a small video clip is going to show up. It's blurry at the beginning, but I think it's going to clear up a little bit. So if you observe from the apex of this cone, tiny drops, they drip down. And when they drip down, they fall onto a rail and get onto this black metallic sheet. And then these drops turn around as they go on this black sheet. So the drops are projected at a certain speed, and when they reach the middle of this black sheet, they turn around through different angles, right? I hope you see that. You want me to play this again? Okay, so here you go. Here are the drops. So the drops, and this is a rail that directs these drops onto a black acrylic sheet. And if you observe closely enough, these drops, when they reach the center of the screen, they turn through different angles. Now, question for the students here: what is the identity of these drops? What are these drops made of? What is your guess? These drops must be of some liquid. So what is this liquid? What could this liquid be?
Liquid nitrogen.
Liquid nitrogen? So, but why is this liquid nitrogen drop bending then? What is making it to bend?
So are there some charges involved?
Charges? Okay, then why does it bend? Yes?
With this, perhaps the cone itself uses some sort of spin or angular momentum.
Now, how is that really? Are you a follower of the law of conservation of angular momentum?
Yes.
Okay, so then it wouldn't be possible. Any other clues? Any master's level student, anyone? So if this cone has liquid nitrogen in it, then think what could be a drop that coalesces on the outer surface of this cone, and all of these drops then coalesce, become a bigger drop and fall down from the apex of this cone. So this drop is a liquid oxygen drop. Liquid oxygen has a boiling point of minus 183 degrees centigrade. Liquid nitrogen has a boiling point of minus 196 degrees centigrade. So inside the cone, the temperature is minus 196 degrees centigrade. The brass material of the cone is a good thermal conductor, so it gets cold. But it's not, the outer surface does not get as cold as liquid nitrogen. It's at a slightly higher temperature. Since oxygen is there in our air, and there's about 20% of air is oxygen, the oxygen in the air finds a surface that is cold enough so that the oxygen in the air condenses. All the oxygen in the air condenses, and they all drip down, they run through the slanting surface of the cone, they coalesce on the tip of the cone, become a bigger drop and fall down under gravity. Now when they fall down, they are directed onto a surface. Underneath the surface, I placed a magnet. The property of oxygen is that it has lone pair of electrons. From its atomic structure, we already know. From the molecular structure, we know it has a lone pair of electrons. Those unpaired electrons impart a paramagnetic character to oxygen. So since oxygen now is paramagnetic, it is maneuvered by magnetic fields. So under the action of that magnetic field, this paramagnetic drop of oxygen changes its direction. Got it? So this is an easy way of creating liquid oxygen, and an easy way of demonstrating that the liquid oxygen is indeed paramagnetic. Now the question is, by looking at this experiment, the liquid oxygen drop is coming and it's changing its direction. Sometimes it passes straight through, sometimes it moves through different angles. Does this remind you of any other experiment that you've already studied, even in your A-levels? Rutherford's experiment. Exactly. So what happens in the Rutherford's experiment is that alpha particles impinge on a gold foil, and since these alpha particles are positively charged, the nucleus is positively charged. The nucleus, when the alpha particle gets close enough to the nucleus, it is repelled, so it changes its direction. Some of those particles move to large angles. Some of them can even be deflected. It's like shooting a cannonball on a tissue paper and getting some cannonballs reflected back. But most of these alpha particles pass undeviated because the nucleus is about 5 orders of magnitude smaller than the atom itself. So this is exactly the same phenomenon but occurring smaller energies. The alpha particle generally has an energy of at least 3 or 4 mega electron volts, but this is something in the order of electron volts. It's a low energy version of the Rutherford experiment, and the interaction that is involved here is not electrostatic, it's magnetic. Now we'll take a video of this phenomenon. Okay, so here is another kind of, some master students tried putting these liquid oxygen drops on a surface of water and seeing how their paths are diverted. But once you take a video of this phenomenon, you can actually plot the trajectories of these drops. And then you can describe. Now a physicist steps in and tries to describe these trajectories. What are the angles? What is the probability distribution of the angles through which these paramagnetic drops are deflected, depending on the magnetic field? One, of course, has to model the magnetic field as well and come up with an equation of motion. The equation of motion looks like this. You solve this equation of motion and you plot the angles of deviation. So now comes the mathematician and the physicist who looks at this video and positional data from this video and tries to make sense of it. So this is the power of video tracking. Okay? Now in another experiment, just to give you another example, I have examples after example today. We take a clutch wire from a motorbike and make it taut, extend it by applying a force on it, and then we have different cameras positioned on this string. And these cameras take videos of the vibrating string. So the string is set into motion with a speaker at a certain frequency. You know there is always resonance, there are resonant modes and so on. So the frequency of oscillation is varied. This tension or mass is known. One would expect that standing waves are formed if the resonant frequency, if the frequency that is applied is equal to the resonant frequency. So now let's look at the trajectory of these strings. These two cameras kind of help us see what shape the string takes. Okay, so the speaker is oscillating the string vertically. However, at small frequencies away from resonance, the string actually revolves or oscillates in a slightly tilted plane. As you increase the frequency, the amplitude of the vibration goes up, and at a certain point, that linear polarization, let's call this linear polarization, the linearly polarized string, which is oscillating up and down in a single plane, it opens up. It starts moving around in an ellipse. The inner size of this ellipse keeps on going up. At a certain point, h, this ellipse starts resembling a circle. This is the frequency at which the vibrating string is in a state of resonance. So in a resonant state, the amplitude is so large that the period of oscillation, that the shape of the oscillation starts resembling a circularly polarized wave. So now the string does not oscillate in a vertical plane or a slanted plane, it starts going around in a circle. And right after you go across resonance, it collapses back into a linear polarization state. Now all of this can be observed only through a camera and through video tracking. You do see the string going around in an ellipse or a circle, but really if you want to make quantitative sense of this, if you want to be trained as a scientist or an engineer or a physicist, you really need to look at the quantitative data. And video tracking allows you to do that. Okay? And then steps in the mathematician or the physicist who would like to write an equation for this and find a solution for this equation. If you do an analytical solution for this equation, you will get these tongue-shaped structures, and the structures, the experimental data closely matches the mathematical prediction. So this is an experiment in nonlinear science, nonlinear physics. You come up, this is a perturbed linear harmonic oscillator, which is no longer linear. Okay? It's called a Duffing oscillator as well. So you do all the mathematics, predict your solutions, plot your prediction, and see whether your experiments match your data. So this is what a mathematician or a physicist would really do. Okay? And that's what discerns a physicist from an observer. Okay? And all of this is possible due to this solid technique that we call video tracking. Now, a really beautiful phenomenon does occur, which is impossible to perceive without video tracking. Now, every string which has been subject to a tension has a certain resonant frequency. Suppose that resonant frequency, just for the sake of it, is 100 Hertz. What if I oscillate at 50 Hertz? What if the stimulant frequency is 50 Hertz, which is not a multiple of the fundamental frequency, rather it's a fraction of it? What if I stimulate at 25 Hertz? What if I stimulate it at 12.5 Hertz? I get a new phenomenon which is called subharmonic resonance. And it's only possible because the string behaves like a nonlinear oscillator. And if I were to solve the mathematical equations, these are my predictions. Okay, I get curves of this kind. And on the top row, I plot my experimental data coming out from clever video tracking. So these new beautiful shapes emerge that resemble the petals of a flower, and that's why they are called Rhodonia curves. Okay? All of this is only possible because you have this master stroke of using a video camera or a camera and getting quantitative data out of it. Okay? A very simple example of an oscillator that is vibrating in a viscous medium, honey, oil, water, In fact, when we started video tracking many years ago, this is the first experiment that we did, and we published this in some journal as well. So there is this damped harmonic oscillator, one of the most complex books that one can ever read, or what I've read, are the books by Lifshitz and Landau. So they have a book on fluid mechanics, extremely terse. So we had to spend months and months of understanding what he really meant and come up with an equation that describes this oscillator inside a viscous medium. Okay, so this is a drag force that acts on this object. Okay, from your basic, probably your A-level physics, you might have come across this drag force, which is called the Stokes force or Stokes term, which is equal to 6 pi eta RV. That might sound familiar to you. But this is the complete expression for the drag force that acts on an object inside a viscous medium. So with the help of video tracking, you can see how damping occurs, and then you would like to combine your experimental data with theory. You can also explore different regimes of damping, heavy damping, light damping, critical, subcritical damping, and so on. All of this is again possible through video tracking. Now this slide, this is a sequence of different kinds of experiments that our students generally do, and some of our master students engage in this laboratory to a deeper extent. So basically what we have is, how do we do experiments of this kind? We have an object or a phenomenon that we would like to observe. We place a camera, it could be a smartphone, a DSLR, a high-speed camera, whatever you fancy, whatever meets your needs. Fast processors need fast shutter speeds or high frame rates, so you would have to use more expensive cameras for that. And generally we employ these lights we call them AC lights. Okay, we can adjust the temperature and illumination, and we would like to take a video of the phenomenon in the presence of this DC light. Turn off the AC lights because the AC lights will give you a flicker in the video. So we generally try to perform these experiments either in the sunlight or artificial light, which is DC. Okay, so this is how you generally would like to do this. Sunlight, by the way, is the best form of DC light. And students can perform experiments of different kinds. For example, a pendulum. One can plot the displacement of a pendulum, the speed of a pendulum. The speed comes out from differentiating the displacement data. And I'll give you an example of that. It's very easy to do. You can write a computer code for that. Let's look at this example of an object that is rolling down an inclined plane. By the way, all the data that I'm going to show you in this slide is obtained from PhysTrack, our software, and different videos that students have taken over many years. So now we have a cylinder that is rolling down an inclined plane, and we put two markers on this cylinder. So we identify those markers as our objects that we would like to track. We can also identify the whole circle that appears in the frontal plane of this video as our object. So we can identify three objects, the two markers separately as well as the whole object. And once we complete, we can also define a coordinate axis and so on. And once the PhysTrack software is run, we get this very rich compendium of data in different frames of reference. We get speeds, positions, accelerations. We can also look at the cycloidal motion of a point on the periphery of the disk. We can get angles. We can find angular energies, potential energies, total kinetic energies. Everything that you study in your mechanics course comes to life. And this is not just simulation. This is actually doing the experiment and observing a real experiment, a real phenomenon, and getting data from it and trying to see if it all makes sense. Yes, please.
So by putting on the marker, you get the rotation
Right. So you can also work with different frames of reference. Our software allows you to transform between different coordinate axes. You can use a lab frame, you can use any slanted frame, you can use moving frames as well. This moving frame in this example is an example of a non-inertial frame. So all of this is possible. And this is what really physics is all about, by the way. Experimental physics is about measurement, getting quantitative data, and drawing inferences from it. And the camera is a great tool to gather data. Now let's look at this video here. Now this might look like a seemingly insidious video that really means nothing, but let's look at it carefully. You see these wall drops, they look like specks of dust. And can you discern that they are moving, jostling around? These small particles are jostling around. Okay? So, any guess what these particles could be? And what is this video showing us? Any guess? Exactly. It's Brownian motion. So what we've done is we've taken a microscope. Under the microscope we put a petri dish with aqueous medium and put some microspheres in it. Diameter is around 10 microns, 15 or 20 microns. The polystyrene polymeric microspheres that are put inside this petri dish, and we just took out the eyepiece and we placed it to the camera, and we take a video of this motion at a certain temperature. Now we can use our software or any other software. We can track each of these particles. There is an ensemble of particles and we can track all of them. Okay? So, in the next slide, I have a demonstration of how this is done, but I'd like to show you a real video, so I'll skip this slide. Finally, we get data of this kind. So, if you look at a simple particle in this ensemble, it shows this random walk. The drunkard man walk. Okay? This is Brownian motion, random motion. And if we look at an ensemble average of all of these particles and plot the distance squared that this ensemble has moved with time, you get a linear curve in complete accordance with Einstein's prediction. Okay? And this is an extract from the original manuscript published in the 1920s by Perrin, who did the first experiments to prove Einstein's ideas of Brownian motion, for which he got the Nobel Prize. And his experiments were painstaking because they were done under visual observation. There were no cameras at that time. Okay? So all of these images were projected on a photographic screen. But now with the help of a camera and a modern compound microscope, all of this will be done relatively easily. In this slide, I would like to show you two objects. One is a disk. So on the left we have a picture of a disk, and we employ a high-speed camera to look at the trajectory of this disk as it is being spun on a flat surface. And the color coding of this trajectory represents the speed. So in our software we have a mechanism to show the color coding if you like to look at speeds. So if you look at this trajectory, it has a very nice floral shape, looks like patterns and all, a beautiful symmetrical object, and the centroid is kind of collapsing inward. Now if from the same object I machine out the inner surface and leave just an angular ring, let's see what the trajectory looks like. Once again, using video tracking and PhysTrack, this is the trajectory that we observe. Now, the interesting bit is that this pattern does not fall into itself. It turns around. In fact, we can do a sequence of experiments by creating a sequence of objects with different sizes for the annular opening. So this is the complete disk. This is the thinnest ring, and we machine out varying amounts of material from the center and do video tracking. So there's a progression from in-grade motion to retrograde motion in all of these objects. Now this is a master's level thesis of how do we explain this motion. And still this is incomplete work as far as I am concerned. We're looking for a student who can actually take this up. Okay? But the purpose to show this to you is to highlight the power of intelligent video tracking. Now there's another object that is called the Wilberforce pendulum. Now it's a classic object. It has never found any interesting use case scenario, but it's a pendulum that oscillates, but it can also turn around. So it can show torsion as well as oscillation. So there are two kinds of modes. One is its oscillation or compression or tension, and the other is its torsion. These are two different degrees of freedom, and they're coupled to one another. A simple linear harmonic oscillator just moves it along a single degree of freedom. Now this has two degrees of freedom that are coupled with one another.
Is it like a bob on a spring?
Sorry?
Is it like a bob on a spring?
It is like a disc. Let me show you what it looks like. I don't have my glasses, so this will have a spring. So it has a spring and a disc. So it can oscillate and it can rotate. Now if you look at the equations for this object, there are two equations. One is its longitudinal motion expressed by z, and the other is its angular motion, its rotational motion. And you can also find a coupling between z and theta through this second, third term. Alright? So now this epsilon is unknown and it represents the coupling parameter. Now you can solve these equations, you can do a complete theoretical analysis, you get this behavior which is called avoided crossings inside this coupled system. These are the mathematical results. And you can also use these results. So each one of these is going to have a resonant frequency. Each of these modes, F1. Sorry. So there is a resonant frequency F1 and F2 or omega 1 and F2, and if you take the squares of these frequencies and then take the square of the difference of the squares, you get this equation. And from this equation, from the resonant frequencies, you can actually determine what the epsilon is, you can determine the moment of inertia as well, and so on. So you just put this in front of a camera and take data with different moments of inertia, perhaps. The moment of inertia is simply the size of this disk, the span of this disk, the mass of this disk. And then you take all of this data and get these rich data sets, which apparently do not make sense because they're so complex. But video tracking allows you to hone into this data, to plunge into this data and make sense of it. Finally, we do a Fourier transform. We convert this temporal data, which is time series, into frequency data. And the step that does that is called a Fourier transformation. So you then take Fourier transforms. So each mode has a single resonant frequency, which is a single peak from one mode. And when you change the moment of inertia, one mode remains fixed, the other mode keeps on moving towards it. Eventually there is an avoided crossing and it starts moving away. All of this is now possible to be analyzed using the data that is available. And then you can make all kinds of plots, find decoupling constants, and so on. Now this is a very interesting experiment. If I take a hot band which is slightly curved and put a blob of water on it. Let's see what happens. So on the left, we have this blob of water on a concave hot surface. Let's take a video of this object. Now if you observe carefully, the outer periphery of this blob is breathing. It's changing its shape. The fingers that are protruding from the blob, they are changing their position, and the overall shape is oscillating. Maybe you video tracking to observe this and come up with a description of why this is happening. Why does this have these 12 fingers or 10 fingers? Is it possible to control the shape and the number of protrusions of this blob? Is it temperature dependent? And so on. Now these are beautiful experiments, very rich experiments, which can be analyzed through video tracking. Now let's look at another experiment, which is one of my favorites. So here, a student is inflating a balloon, opening a valve. The balloon is connected to an air compressor, and the balloon expands. Now what is the pressure inside this balloon as a function of its volume? Assuming that the balloon is a sphere, or even if it's not a sphere, we need to have some relationship between pressure and volume. So we take a video of this phenomenon and write a computer code. This computer code is slightly more complex because now we're looking at an extensible object which is non-rigid. So we make a video of this expanding balloon, and we also have a pressure sensor. So here is a picture of a pressure sensor that we've made. It's called PhysTrack. It's connected to the tubing, so it measures the pressure inside the balloon. And it puts the reading on a computer. And the reading is here. It's visible on the computer screen. So now our video tracking software is capable of converting this data into a string of numbers. This is called optical character recognition, OCR. So now we're looking at the video of this object, and from the video of this object and the shape of this object, deciding what the radius of this object could be, and OCR, which takes the pressure, we can plot the pressure versus the radius. Now does the pressure versus radius or pressure versus volume graph obey Boyle's law here? No, it doesn't. Because this is not an incompressible fluid, and this object is placed inside an extensible elastic medium. So it does not obey Boyle's law. In fact, the nature of this curve tells great deals about the elasticity of the material that makes up the balloon. You can cool the balloon, put it into liquid nitrogen or ice, and redo an experiment and see how the polymers inside the balloon change. Do they extend further? Do they extend less? So all kinds of experiments can now be done. And then there are sophisticated mathematical models, such as the Ogden model and so on, that predict what the shape of the pressure versus radius is going to look like. One of my master students actually did a year-long project on this. All of this is enabled by video tracking again. Okay? Now here is just one more example. So if you observe this video, I have an inverted U-shaped glass tubing with two bulbs and a valve that can interconnect the two sides. And I put a soapy bubble on each of these glass bulbs of different radii, and then connect the two bulbs together. So I have a bubble here and a bubble here. So suppose, let me ask you a question. If I have a big bubble here on the left and a small bubble here on the right, and the two are disconnected in the beginning, if I connect the two, what's going to happen to the big bubble and what's going to happen to the smaller bubble? How will their sizes change? They will equalize. Okay, let's see. So now we take a video of this phenomenon. I want to speed this up. So here is an experimenter putting soap inside each of the bulbs. Hopefully bubbles are going to form. So here is one bubble, and the two valves are disconnected. Now the two valves are disconnected in the beginning. So here is one bubble, here is another bubble. Okay, so they start off at different sizes. Now the two arms are connected. So what's happening is that the smaller bubble gets smaller, and the bigger bubble gets even bigger. So this prediction that the two sizes are going to equalize is not true. And that's because the pressure volume curve has this strange kind of shape for any balloon. There's a model that describes how these extensible media behave. That model is called the Laplace's model. So look at this curve. It goes up, positive slope, then it has a downward slope, and then a positive slope. So depending upon which regimes you operate in, a bigger bulb can become bigger, and a smaller bulb can become smaller. The two can also equalize if the two bulbs are in different regimes of this Laplace curve. Okay? This is the beauty of physics. This is why we should love physics. This is why this is so interesting. Now, another seemingly simple phenomenon of a candle burning. If you look at how a candle burns, so this is a burning candle. If you look at the shape of this edge of the candle and track it with a video, this shape has a universal behavior, and it depends only on the diameter of this candle. With video tracking, you can explore this. Okay, so you can plot the angle that this slanted edge makes with time and come up with a description of why it is behaving this way. Now let's look at another really interesting experiment. Let's look at how fluids disperse inside a medium. Now in this top video, this is an aqueous medium with some olefin in it, some oil in it, and on top of this oil we drop some ethanol, which is colored. A mixture of ethanol and water which is colored. And see how this drop diffuses or breaks up. What happens to this? Okay, so let's see. By the way, all of these phenomena, they're not new phenomena. These phenomena have been known to humankind for centuries. They're not new phenomena. The power of physics is that even old phenomena get a new meaning. Now we are able to explain phenomena that have already been known to mankind. Okay, so let's look at this insertion of a drop on this aqueous surface. Simply a camera, good lighting. Okay. Here is Elisa who performed this experiment. So this is what's happening. So there is one central mother drop which is expanding. But as it expands, its outer rim breaks up into these smaller drops. And the daughter drop, a larger surface is created, which expands. But the mother drop then starts to shrink until all of it has broken down into smaller drops. Now this effect is called the Marconi effect. And it also describes why you get these nice looking shapes on your coffee cups and so on. What's really happening is the ethanol or the alcohol that is inserted inside this liquid has a certain evaporation rate. And it's evaporating because it's volatile. It has a small vapor pressure. But as it evaporates, its surface tension continually changes. So because of diffusion, this mother drop is going outward, but as it is going outward, it's also evaporating. Now that creates a difference in the concentration of ethanol from the center towards the rims. That difference in surface tension is really a difference in energies. And because of this difference in energy, this gradient in energy, there is an outward flow. But on the outer rails of this mother drop, the drop cannot sustain its shape. It cannot, it's not rigid enough, so it breaks up into these smaller drops. Okay, so this is an explanation of the Marangoni effect. Now we can, with video tracking, we can plot the radius of the mother drop with time. We can plot the radius of the daughter drop with time. And we observe this extremely interesting temporal behavior. And we also kind of build a model, a mathematical model which is not purely diffusion. It is diffusion intermixed with the concentration gradient caused by the gradient in surface tensions, and try to explain what's going on. Okay? All of this is now only possible with video tracking because you have a rich set of data and you have some software, some algorithms that can analyze your videos. If you have a needle or a tip and you touch a drop of liquid on its tip, the shape tells you everything. From the shape of this drop, we can find out the surface tension, we can find out the density of this object, and so on. So don't take shapes lightly. Shapes of fluids are really important. Now this is not an example of video tracking, rather it's an example of image processing. So this is, I think, experimental physics at one of its best. So I just want to show you that this data has been acquired by a large number of people over the years. This group of ours, which is called the PhysTrack. Now, in the next 5 minutes, I would just like to show you how this work can be done using our software. I'll just take a sample video and try to process it in front of you so that you're able to do your homework. Okay, so the video that I'm trying to test is, first of all, I will turn on the lights. So I'm not going to do all of it right now, but I turn on the lights, I take my camera here, I might have to use 2 lights or any other form of DC light, and I look at my phenomenon. Here my phenomenon is the sequence of pendulums. Okay, one strikes the other, the second strikes the third one, and so on. This is generally called the Newton's cradle. I don't know if it has anything to do with Isaac Newton, but still it's called that way. So I displace one of the blocks and I track the motion of the Okay? Now let me show you how we can do this using our software. Just to give an example and just to give you some confidence that all of this is pretty easy. Alright, so now I turn to PhysTrack. Alright, so I download the software from the website. We'll send you an email from where this software could be downloaded, but you're welcome to use your own softwares as well. So I run the software using a command called run visit. Can you see, or do you want me to increase the font size a little bit? It's fine? थोड़ा बड़ा कर दूं? ठीक है? So I run wizard. Now what I want to do, I want to do general purpose tracking. So there are different algorithms available, different codes available. And if you're not sure, you can just use the general purpose tracker, which is a fit all kind of version. So I use the general purpose tracker, I open it. Now it's asking me, I need to open a video file, right? This shows which video file you want to take. So I take my video, I put it onto the computer somehow, through data transfer cable or by some other means. I open my video. Now the video I want to focus on is a video obtained from this phenomenon. I already have acquired a video from this setup. Here it is, grade L3. I open the video. Now you want to time everything, you want to find speed, you need to know this video is a sequence of images timed at roughly regular intervals, not precisely regular intervals, there's always some timing jitter. So it asks me how many frames have been shot per second. And in most cases, the video reader automatically detects the frame rate. So it's 240 frames per second. So we use the high-speed smartphone or high-speed camera for this purpose. So I put in the number 240. In this case, it's already there. And now it opens the video. Now this is a scene of the video and I can preview it here in the software. Let me preview this video. Okay. So it goes frame by frame by frame. Let me forward this a little bit. Here is the experimenter holding a bar. Let me forward this a little bit more. Here the bar is set into motion. It strikes the cradle, transfers momentum to the ball at the other extreme. All of these balls have approximately the same mass. This comes down. It transfers back its momentum to the extreme ball. And these amplitudes are going to drop with time. And eventually, all of this object is going to show some nonlinear behavior. It's going to swing a little bit. Okay? So now what I need to tell this software, this tracking algorithm is, where do I start my analysis from? Okay? So I want to start, I want this hand to go out of the frame. Okay. And I want to start, say, my analysis from here. So I mark this frame as the in frame. Okay, mark in frame. And then I preview. Okay, and the whole video plays itself. Now I need to mark a frame at the other extreme, where I want my analysis to finish. Okay, so I fast forward this a little bit. Let's say I want to stop here. We want the oscillational diagram. So I mark this as the out frame, mark out frame. Now in this video, when I do the video tracking, this is a large size video. I don't want the video tracking software to be concerned with the other parts of the video that have nothing to do with the motion. So I want to define a small region of interest. So I only crop out that part which is of interest to me. Okay? So I click on reset crop region, the cursors change, and now I can define a region of interest where motion is likely to occur. So this is my region of interest. So when video tracking is going to take place in this software, it's only going to be concerned with just this region. It's going to kind of ignore everything else. So now I close this window. Now I want to see which objects we want to mark. Okay, so I click on mark objects to be tracked. Now suppose I can mark all of these 7 objects. But suppose I just want to track 5 of them. I want to track the rightmost 2, the middle one, and the leftmost 2. Okay? So I mark those objects. This software, by the way, can automatically detect moving objects as well, but that does not work all the time. It works most of the times, but if the video quality is low, if there are many moving objects, it kind of falters as well. But let's manually mark the objects in our case. So I say manually mark an object, and the 5 objects I want to mark, I put these boxes around them. 1. So the coordinates, the centroid of this first object appears in this window. Now I have a second object. I mark it. A third object which I take to be the middle object, I mark it. The fourth object, the penultimate object on the left, and the final object, which is the extreme object on the left. So now I've marked my 5 objects. And I would like to tell tracker that please track these 5 objects for me. So you run this algorithm. I close this window and I want to run the object tracker. Okay, there's an algorithm that does that, which is a commonly used algorithm in computer vision. So now I want to begin the tracking. I want to update the image and show a trail of points as well. Okay, let's see if my software is able to do that. So it's begun. Now it has put different colored boxes on each of the objects and is tracking them. It's running at the moment. It's also giving me a count of the frames that have been processed. It's also giving me a count of the time that remains. Okay? So this is a high resolution video, lots of frames. I think we have 3,000 or 4,000 frames here, I'm not sure. But it's going to track all of these objects. And if you observe carefully, since I have the short trail feature on, it's also showing a trail of points from the previous 10 or 20 frames. I can hide this feature as well. So let this run. Be a bit patient. We put all the responsibility on our processor. Any questions would you like to ask in the meantime?
You mentioned that if we transfer almost instantaneously to let's see point one, even though the frames are running at like Facebook. So if I go
It's not really instantaneous, no process instantaneous, because instantaneous would mean that the pulse is infrared. So every contact happens over a finite period of time. So in textbooks it's instantaneous, but in reality it isn't.
if I would increase the number of balls, so the time would increase or the moment.
Yes. Yes. Yes.
Sir, I have a little curious question regarding limitation of these video softwares. Sir, let's say, for example, at quantum level, somehow
Quantum level?
Yeah, somehow use quantum computers to get the orbitals of electrons. In those circumstances or conditions, will those softwares work, or will there be any limitations?
So you're looking at the quantum motion of electrons.
Yes.
Well, you can't really picture a wave function in the conventional sense. The quantum world is totally different. There is no such thing as a picture of the electron, as far as I know. Okay? Yeah, the Heisenberg uncertainty is always at you cannot beat that. But there is no such thing as, so when I teach quantum physics or quantum physics, the question that I ask is, where is the electron? You cannot answer this question because this from quantum mechanics, this is not a good question.
But sir, can we still use softwares to, let's say, analyze their wave functions and predict orbitals?
Yeah, you can. You can use microscopic techniques. For example, a scanning tunneling microscope looks at the wave function of electrons and atoms. Alright, so it's done. Do you want to filter out some wrong points? Let me show you how this is done. Okay, I want to filter out some wrong points. Let me show you what this means. So there are 3,900 frames. So if I preview this, so really what's happening is that with each marked object, there is a collection of points. So these are the red points, the green points here, the blue points here, and the software really looks at the centroid of all of these points. So since it's a large extended object, it has put a large number of points, 10 or 11 points on each object. And it really looks at the centroid of all of these points and identifies that with the object. So in some cases, if this object is moving and all the points remain on side the blob, is fine. We don't want to remove any tracking point. But observe this point at the outer periphery, this red point, it has slightly moved out of the object that you want to track. So I want to exclude this from the analysis of where this object really lies. Okay, it's like an outlier. So if I want to do that, I can do that, surely. So let me fast forward this a bit. Yeah, but that's not always possible. In real experiment, you can't have point masses. You'll find to a very large extent all of these points are stitched to the okay. So observe these points at the outer periphery that have been unstitched from the object. Let me remove those. So just to give you a sense of how this removing of the unwanted points occurs. So I click on remove track points and select those points I want to remove. They go away. So they are not considered from the analysis because the lighting conditions, the size and extent of this object is such that some of the points have wavered outside. So I close this now. And now I want to define, if I want, I can define a reference coordinate system as well. So I can do it without a reference coordinate system, then it will give me answers in terms of pixels. But now let's use millimeters or centimeters and use a proper coordinate frame. So suppose I want my origin to lie in the middle of the central ball. Okay? So here I click on reset origin and it creates an x-axis and a y-axis automatically. Now I want my x-axis to be in a certain direction. I want it to be along the horizontal direction. So I click on reset x-axis and move the cursor here. Click here. So my x-axis is now from left to right. But I want my y-axis to be upwards. I can move with this as well, but I want to have a certain human-friendly definition of the coordinate frames. So I click on toggle direction. My y goes up. My x is in the conventional direction. So I want to feed this to my algorithm. And I also want to work in centimeters or millimeters instead of pixels. So suppose I know the size of each of these objects, say it's 5 millimeters or 10 millimeters. I reset unit marking. I draw a scale and put in this length here in the units that I want to work with, 10. Okay, and I close this.
So you could also change it into like some other coordinate system, polar coordinate, because it's some certain kind of rotation happening.
I cannot change this into polar systems, only orthogonal coordinates. But then I'll have to do that in software, okay? in my app. I can need to write a computer code for that. Okay, so now this is all the data that has been created. If I look at trajectory, so let me see what this output trajectory is. Trajectory is a structure which has 5 sub variables, TP1, so there are 5 objects. Okay? So let's look at one of these objects, trajectory.TP1. This is an object that has a sequence of x's and a sequence of y's. And each one of these variables is of length 3901. That's the number of frames. If you look at the time variable also has 3901 points. So you have a time variable and you have x and y's for each of the 5 points. And all of them are stored in the structure called trajectory. So trajectory has all the position variables in terms of your millimeters or centimeters, whatever you define, according to the coordinate frames that you defined.
Kind of metrics.
It's kind of a structure, yes. It's called a data structure. So now what we have is, I've already written a computer code which picks up x1 and y1, first object, x coordinate, y coordinate, second object, third object, fourth object, and then it plots everything. So I've already written this code for you. And then in another sequence, we've also written a code which is packaged with the PhysTrack, which takes derivative of any sequence, So the script that does that is called deriv. So what deriv does is that it takes the time and the variable that you would like to differentiate. And when you do numerical differentiation, there is an order to it. First order, second order, third order. So I do first order numerical differentiation, which takes 3 points in the sequence, and there's an algorithm and gives me one value. But then the number of time points also changes. So I get a new time for the derivative. So I put the times and the derivatives in these new arrays. That's what I've done over here. Finally, or adjust the plots. I'll share this code with you on my diary. So let me run this and see what I get. Okay, so I get a sequence of data. Everything works out really nicely. First of all, what I've plotted is the x position of the 5 blocks. This is the middle block, which is hovering around 0. At some point, it slightly starts showing some oscillations. But these are the bonds to the right, positive x's, and these are the bonds to the left. And these are the y positions, because the bond also shows a y displacement, not just x, but y displacement. Okay? And the y displacements are generally smaller than the x displacements. By the way, these units are not x, these are not pixels now, these are really the millimeter or the centimeter that we find. Okay? Here are the speeds. Okay? It's not really simple harmonic, but still speeds make sense. And these are the speeds along the x direction for the 5 blocks, and these are the speeds along the y direction along the 5 blocks. Since the y positions are smaller, the speeds along y have a greater uncertainty, so they are more noisy. Okay? But generally, when you take differentiation, the noise goes up. And when you take an integral, the noise goes down. Okay? So here I focus on the extreme verbs, leftmost and rightmost over here. And here is their speeds. Now what I could do is I could plot the kinetic energy of all the verbs. The kinetic energy is half m v squared. Now v has a vx component and a vy component. So v squared is really vx squared plus vy squared. So once you have the vx and the vy, you can find the total energy, the kinetic energy of each bond. And each bond, by the way, you need to know the mass as well. So what I'm plotting here is the kinetic energy divided by the mass. Okay? I'm plotting the speed squared. So if I zoom in onto some region here, so you get this beautiful looking graph. The green object has one of the objects which is to the left has some kinetic energy, and that's when the blue is 0, when it's silent. So when the green blob moves, the blue doesn't move. So the leftmost blob generally moves, the rightmost blob doesn't move. When momentum has been transferred, the rightmost blob starts moving and the leftmost blob comes to standstill. So you can see this toggling of kinetic energy between the left and the right. Okay? Green goes up, silenced. At that point, the blue goes up. There's no green. When the blue is silenced, the green goes up. That's what we observe over here as well. But now we have precise values, estimates for the kinetic energies. You can also plot the potential energies. Now the potential energy is mgh for each bond. So h now is how high are you from the basal line. And that will be an angle. So from the angle theta, which is this inclination angle, you can find out how high you are if you knew the length of this ball. So the height is really L times 1 minus cosine theta. But if theta is really small, you can approximate the height to be y. Okay, so I've taken, in this example, I've taken mgy as the potential energy for each ball. So I can also plot the potential energies, right? So this is a nice curve, this undulatory pattern that you see for these balls. Okay? And I can also plot the total energies. I can sum up the kinetic energies and the potential energies for each of these 5 balls and see how energy is being lost inside the system. Because there's always damping, the sound is being produced. There's a lot of non-conserving channels by which energy is being dissipated inside the Newton cradle. It won't run forever. So you want to see how this energy is being dissipated. So here I plot the total kinetic energy and the total potential energy of the system. Both of them are oscillating and they are damping. And you can write a mathematical model to describe this damping. Finally, here are the potential energies and the kinetic energies drawn together. Anyway, so this is what I wanted to kind of highlight today. Now, lab 1 students are required to do the following. Come up with any experiment that you like. An experiment doesn't have to be in the lab. Go home, look at the examples that I mentioned at the beginning. See any moving object, colliding object, falling object, turning object, running object, anything that you fancy. Take a video and track it. Either using PhysTrack or one of those software that are available such as Tracker. There's a software called Tracker which is very popular. Okay, so if you are felicitous with MATLAB, good at MATLAB, you can use PhysTrack as well. Alright, so any questions before we break the session? So you have to submit your assignment next week before your lab. 2-3 pages only. Write what you've done, main results, and send in your video. So try to make short videos. So drop your video in your LMS Dropbox as well. Okay, just 2-3 pages of what you've done. Okay, you kind of click on this complete downloadable package. If you want some sample videos as well, you click on this. This is a zip file. Okay, so you download the zip file into your MATLAB folder, add that folder to your path, and type in run wizard. It will kind of all the steps that I've shown you will automatically appear. Okay, so you just download the zip file. It has all the MATLAB scripts. You don't have to write your own script, just use this. Any other questions?
Sir, what about the code that you use to write on MATLAB? Do we get on diary?
I will put that code online, but you'll have to write your own code too. Once you have the trajectory data, you'll have to write your own code of what you want to do with that data. I'll just give you an example, but you'll have to write your own code. So what PhysTrack does, it gives you X and Y's for each of your mark points. That's all. That's what you need, really. Yes, please.
Do we have to do this at home or do we make use of the research in the lab?
I think you should try to do this on your own.